Hello and welcome. In this section of the course, we will learn all about cycle detection and graphs. We will first look at why cycle detection is useful and explore some popular applications. We will then explore a common cycle detection technique that builds on the depth-first search algorithm. Finally, we will examine Floyd's algorithm, which is used to detect circular buffers. Let's first get started with this video on practical applications. We will first have a quick summary to see what a cycle looks like, and then explore some of the common practical applications for cycle detection. Here you see an example of a directed graph, which contains a number of cycles. A cycle is a path through our graph where, if followed, it takes us on a loop. Basically, we end up on the same node where we started. Here is an example of a cycle in this graph. On the path marked in red, if, for example, we start from node E and follow the path, we would end up back on the same node. Here is another example of a cycle on the same graph. And here is a smaller one involving just two nodes, J and F. A cycle can also involve just one node. In this case, node J has a self-edge, from J to itself. Not all graphs contain cycles. Tree structures, also a type of graph, don't contain any cycles by definition. Trees aren't the only types of graphs that don't contain cycles. Here is an example of a directed graph which doesn't contain any cycle. Following any path on this graph will not result in a loop. This type of graph is called a direct acyclical graph, or DAG for short. The problem we are trying to solve in this section is, given a specific graph structure, we want to determine if that graph has a cycle or not. There are various real-world applications for this problem. Let's have a look at a common one. Consider a train moving along a rail. It stops at an intersection as it has to wait for a second train that is currently using this intersection. The second train also has to stop because the next rail intersection is occupied by a third train. This third train has to wait for a fourth one, currently stopped because it's waiting for the first train. This is what is called a deadlock. We have a number of processes, the trains, each holding a resource, the intersection, and waiting for one another. This creates a situation where each train is waiting for the next one in a circular fashion. It's important to realize that the train driver doesn't know that he's in a system stuck in a deadlock. From his point of view, he is only waiting for a release of the next intersection so the train can move on. In situations like these, we need an external monitoring system that detects when a deadlock occurs so it can raise an alarm. In this example, one of the trains might need to reverse. This is where graphs come in handy. We can model the processes, our train, as separate nodes. In our previous example, we had 4 trains. Here, we have labeled them from A to D. We can also represent the 4 shared resources, or 4 intersections, as nodes. Initially, train A requests to use intersection 1. We model a resource request by drawing an edge from the process to the resource. Since intersection 1 is free, train A can use it. In technical speak, we say process A has acquired resource 1. We represent this by drawing an edge from the resource to the process. The train moves along, and while holding the intersection 1, it requests to use intersection 2. However, intersection 2 is currently being used by train B. Train B is also waiting for intersection 3, which is being used by train C. You can see where this is going. Train C is waiting for intersection 4, currently in use by train D. which is in turn blocked by train A on intersection 1. And here we have our graph cycle. If we model our train system using a graph, we would just need a clever algorithm that monitors this graph and detects cycles. This is one common application for cycle detection, that of monitoring for deadlocks. A deadlock detection is of course useful. Deadlock detection is of course useful not just for trains, but many other scenarios, including, for example, databases and operating systems. A simple deadlock can occur when you have two processes A and B, and two exclusive resources. Each of the processes hold a lock to one resource, and request access to the other, resulting in a deadlock. Again, in this scenario, the operating system or database server can model the system using graphs and monitor for possible cycles. There are many other applications for cycle detection. In code analysis, we can write algorithms to help find trivial infinite loops to discover possible circular dependencies. In computer networks, configuration can be analyzed to ensure there are no circular routes. Cycle detection also has applications in bioinformatics. Biological systems can be monitored by graphs, where a cycle would show a feedback loop in a system. It is clear that determining if a graph is cycling or not is very useful. In this video, we have seen some examples of cyclic graphs and later saw some applications for detecting these types of graphs.